When we take a look at a few examples of directing effects, we simply need to be able to identify each substituent that's on our benzene as a strong activator, moderate, weak activator, weak deactivator, moderate deactivator, strong deactivator. 6 choices, right? We have to assign each of them to each group, right? When we look at anisole, and we look at sulfonating anisole, we see that anisole is a moderate activator. And we remember that all of our activators are ortho-para-directors. And so if we're going to treat this with fuming sulfuric acid, that's the reagents we need to sulfonate a position, we see that anisole has more than 4 atoms on its directing group, as it were. So presumably, we're going to see that it's a para-director then. It will produce both ortho and para, but para will be your predominant product. We're going to see that we're going to end up getting our sulfonation to happen at the para position. Not only is our directing group sterically inhibiting, but the electrophile we're putting on, the SO3, also is kind of bulky, right? We have sulfur with 3 oxygens on it. Although that is 4 atoms, it's still kind of a iffy situation there. Sulfur is a pretty big atom. So again, we have kind of steric effects drawing it to the para position. And so if you think about how we did this problem, we past tense here. We identified the substituents on the benzene, and then we classified as, for example, a strong activator, moderate activator, weak deactivator, moderate deactivator, or strong deactivator. Remember, those are the 6 options we have. So whenever we're going to be doing a problem where we're taking something that already has a substituent or multiple, we need to identify all of them and then classify them as what type of activator or deactivator they are. And so, fairly straightforward with just one substituent. But now our anisole has a sulfonic acid on it. What's going to happen now? Let's find out. If we take that anisole, the parasulfonyl anisole, that is, and we treat it with, say, how about we chlorinate it? Because why not? Let's chlorinate it. Let's do a chlorination reaction using our catalyst. When we have multiple groups, what do? We see, aha! We have the anisole, or rather the methoxy group. That's a moderate activator. We have the sulfonyl group, sulfonic acid. That's a moderate deactivator. So what happens? I'll tell you. The strongest activator guides the reaction. So we need to follow this hierarchy. Our strong activator will always make the call. Our strongest activator, whatever it may be. These are all relative to each other, right? A strong activator is stronger than a moderate activator. A moderate activator is stronger than a weak deactivator, right? This is a hierarchy. And so I'm going to actually replace all these commas with greater than signs. We need to figure out where they are in our ranking. We have a moderate activator and a moderate deactivator in this compound. The strongest one towards activating wins. So our moderate activator wins. And our moderate activator says, I am an ortho-para-director. And as a result, we should put our chlorine ortho or para. As we see here, that sulfonic acid is already occupying the para position. And so if the only thing left is ortho, that makes our product pretty easy. We could say, aha, it's our benzene. We've got the rest of the stuff on here. And now we have a chlorine. Ortho to our strongest activator. Even though it's not a strong activator, it is our strongest, relatively speaking. So let me write this out in, let's use a fancy green. Yes. The strongest, remember this is a relative term now, strongest activator guides an electrophilic aromatic substitution reaction. It will guide your new substituent to where it wants to go. So if you're stuck between a moderate deactivator and a strong deactivator, it's going to be meta to your moderate deactivator, right? Whatever that may happen to be. If you've got a weak activator and a strong deactivator, it's going to go ortho or para to your weak activator. Always look what's farthest to the left on this list of whatever substituents you may have. And then you have to decide which one's strongest. That's the one that's going to guide the reaction. And then one more thing we have to think of, because it's never enough, right? It's never enough. Keep sterics in mind too. So we might think, okay, well, we've got, how about the following? We've got this diisopropyl benzene. And I want to nitrate it. So I'm going to use nitric acid and sulfuric acid. And we have to think, where's this going to go? Well, we have options. Of course, this is a symmetrical molecule, so that's going to help us out a little bit. But let's identify our substituents. You see there are both isopropyl groups, so this one is a weak activator. It's an alkyl group. This is a weak activator. They're both weak activators. What do we do? Well, first off, will not give you more than one of the same type, generally speaking, unless they're identical, like they are here. With they're both weak activators, neither one wins, and because they're symmetrical to each other, there are symmetry positions here. Just keep these things in mind. We have two options then, where we're going to put our nitro group. Let's take a look at those positions. And you'll see that there's only two because of the symmetry. We can go ahead and draw them all. We can put it ortho to one, para to another. We can put them, that nitro group, ortho to both of them. Or we can put it, again, we're not going to put it meta to the isopropyl groups. That would be quite silly. We know both isopropyl groups are ortho-para directors, so one of them should win, right? So we have really three positions, we can say. Remember, we always want, for an isopropyl group, they should be ortho or para. So notice that on that top right molecule, that new nitro group is ortho to the left isopropyl and para to the other one. And the bottom right molecule is the same. It's para to one isopropyl group and it's ortho to another. In fact, these are the same molecule anyway. So because of symmetry, right? You just flip it around, poof, now they're the same molecule. So really, we only have two choices, right? We can put it on that down position, ortho to one, para to the other, or we could put it in between. And when we see, okay, well, it's ortho to both, seems reasonable. Seems reasonable. It's ortho to both positions. Sterics, isopropyl groups are bulky. They will not allow that position to be gone after, unfortunately. So it comes down to sterics, right? So we had the choice of putting that nitro group on one of two positions, essentially. We could put it kind of ortho to one, para to the other, or ortho to both of them. But ortho to both of them puts it in between two bulky groups. And remember, isopropyl groups are pretty big. There are quite a few atoms. And they're rotating, so they're just like, nope, don't come near me. I am propelling here. Nothing's going to come in between us. But those other positions are like, I can kind of sneak in there maybe. Still not ideal, of course. It's a hindered group, right? But the electronics will always dominate. And then when there's a tie of electronics, what I mean by electronics dominate, by the way, we're not going to put this on a meta position. We're never going to put something meta to an ortho-para director unless there's absolutely no other choice. So electronics always dominate. But after that, if we have electronically similar processes, remember both these positions were ortho or para to both substituents, then sterics come into play. Then we worry, okay, probably not going to go in between the isopropyl groups because the sterics will prevent that from happening. And so, this kind of idea of reacting all of these benzenes in EAS is something that's going to take a lot of practice, do a lot of problems, figuring out where things are going to go, what substituents direct things where. And then the ultimate goal of this is, can I give you a substituted benzene and ask you to synthesize it from pure unsubstituted benzene, naked benzene? That's the real goal here. If you can do that, you have mastered the objectives of this chapter. So far, at least. And that's what we'll look at in our next video.